We're going to shift gears for a little bit. What we've done up till now really has been to calculate improper integrals. I mentioned early on in the course that we would get to a point where what we were doing was not really computational, that it was going to call to mind more the proofs that you did in geometry, like the two-column proofs, where you would try to prove the two triangles were congruent without ever measuring the triangles. So we get to that point in the course. We're going to start making these logical arguments, and this course is going to become a lot more proofy than it's been up until now. So this is the first principle that we're going to encounter along those lines, and it's really a template for something that we're going to be doing for the next several weeks, really. So it's worth getting a handle on it. The first is going to be the comparison test for improper integrals. So what you want to do is imagine that we have two functions f and g, where the two functions meet the property that they are both non-negative, and g is greater than f for all x in some interval from a to infinity. So if that's true, then if the integral from a to infinity of g of x converges, then so does the integral from a to infinity of f of x. And if the integral from a to infinity of f of x converges, then so does the integral from a to infinity of g to x. It does make a difference which order these are in. For example, if I know that the integral from a to infinity of f of x converges, there's nothing I can say about the integral of g of x. And I'll show you why. This is the way you want to understand this. I've drawn here two curves, two very simple curves, y equals f of x and y equals g of x. G is in blue, y is in purple, and we'll notice that this does meet the condition specified above, where 0 is less than f of x is less than g of x for all x in the interval a to infinity. In other words, everything to the right of a. Okay, now look at the yellow area. In other words, the yellow area here is equal to the integral from a to infinity of f of x dx. Now, I want you to imagine that the integral that this integral diverges. In other words, it doesn't equal a finite number, it's infinite. Well, look at what we have here. The yellow area is going to have to be smaller than the area under the blue curve. In other words, the area under the purple curve on the interval a infinity has to be less than the area under the blue curve on the same interval. Why? Because the blue curve is strictly higher up than the purple curve, so that's the only thing that would make any sense. Well, if the yellow area is infinity, and the area under the blue curve has to be larger than the yellow area, then there's no possible way that the area under the blue curve could be a finite number. So that means that if the yellow integral if the integral that represents the yellow area diverges, then so would the integral of y equals g of x of the blue curve. That's precisely what we see here in conclusion 2. I'm doing these in reverse order just because it was sort of easier to show by a picture that way. So in other words, if f of x diverges, then so does g of x. Now, consider it the other way. Let's suppose that the area under the blue curve converges. In other words, even though it looks pretty big, let's suppose that this striped area here, which is a to infinity of g of x dx, let's suppose that that converges. In other words, it equals some finite number. Well, since the yellow region has to be strictly smaller than the striped purple region for the exact same reason that we just talked about above, it would make no sense if the striped purple region could be a finite number, but the yellow region was infinite. So that means that if the purple region is a finite number, the yellow region is going to have to be a smaller finite number, and therefore that's the argument that if the integral of g of x converges, then the integral of f of x also has to converge. So that's of course what you see in conclusion 1 here. So this is a sort of geometric slash algebraic argument about how if one integral converges, then the other must also, or vice versa. Now the interesting thing is, what happens if we say that if the integral from a to infinity of f of x dx converges? Then what can we conclude? In other words, if this yellow area is finite, what can we conclude about the purple striped area? This is the thing that most people find so hard to grasp. The answer is nothing. Why? We know that the yellow area comes out to a finite number. There are a lot of numbers. There are a lot of things that are bigger than a finite number. Let's suppose the yellow area comes out to 10. There are a lot of things that are bigger than 10. 11 is bigger, 12 is bigger, 15 is bigger, a million is bigger, and so is infinity. Except that if it's infinity, then the blue integral diverges, and if it's something less than that, then it doesn't. The point is, it's not that we're saying that it's not that we're saying that the purple that if the yellow integral converges, the purple striped integral doesn't converge. The point is we don't know anything from that fact. And this is a crucially important point as we go on to the proofy part of the course, is being able to not only draw the correct conclusions, but recognize when there is no conclusion to be drawn, when you just don't have enough information to draw a conclusion. This is sort of the beginning of that situation. So we're going to show how to use the comparison test by solving this problem. We're going to show that the improper integral from 1 to infinity of 1 over square root of x cubed plus 1 converges. Now, you're probably going to say, oh, why don't we just evaluate the integral and see if it comes out to a finite number? Take my word for it, although square root of x squared plus 1, we learned in trig sub how to do that problem, square root of x cubed plus 1 is really hard. You don't want to do that. So this is the key to understanding this is we're going to be able to show that this integral comes out to a finite number, even though we're not actually going to find the finite number. We may not even be able to find the finite number, but we're still going to show that it comes out to 1. So here's how we do that. What we want to do is first make this observation. Let's look at the denominator. The square root of x cubed plus 1 is, we want to make it something, we want to compare it to something that's kind of similar to that, but simpler. So it's certainly correct to say that the square root of x cubed plus 1 is greater than or equal to the square root of x cubed, right? If I add 1 to something, I'm going to get a bigger number than if I don't add 1. So that's certainly true. And most importantly, it's true for x greater than or equal to 1. Why do I care about that? Because that's where the interval of integration starts. It starts at 1 and goes up to infinity. So I want to know this is true for all x greater than or equal to 1. Okay, so using a little algebra, if x cubed plus square root of x cubed plus 1 is greater than or equal to square root of x cubed, then 1 over the square root of x cubed plus 1 is less than or equal to 1 over the square root of x cubed. Next thing to note is that, first of all, these are both greater than 0, greater than or equal to 0, but actually greater than 0. And finally, this last expression is equal to 1 over x to the 3 halves. Now, why did I do that? Notice what we have here. We have the integrand in a p integral, and we already know what its convergence properties are. So what we can say is that we have, let's just clean this up a little bit. We have 0 is less than or equal to 1 over square root of x cubed plus 1 is less than or equal to 1 over x to the 3 halves. In other words, I'm going to skip this one here. I'm simply going to note that this integral is equal to 1 over x to the 3 halves. Now, in terms of the comparison test that we did a little bit while ago, this is f of x and this is g of x. Okay, now, what do we know? We know that the integral from 1 to infinity of dx over x cubed over x to the 3 halves converges. How do we know that? We know it because it's a p integral where p is equal to 3 halves, which is greater than 1. And we know that if it's a p integral with that property, we know it converges. This is why we covered p integrals and what their convergence properties was, so we could compare them to other integrals. We can say, therefore, once again, I think you've seen me use that with the 3 dots. It means therefore. It means therefore. Therefore, we can say that the integral of from 1 to infinity of dx over x cubed plus 1 converges by the comparison test. Why? Because we know that its integrand is less than something that converges. So the picture that applies was this one. It's like the 1 over 3 halves was 1 over x to the 3 halves was the blue function, and 1 over square root of x cubed plus 1 is the purple function. If the blue function adds up to a finite number, which we know it does because of the p integral property, we know that the purple one has to also. So we have now proven something, the same way that you prove something in geometry with the SAS postulate. And when we prove something, we end it this way. You'll see this in math textbooks. We end it with a little box like that, which kind of means the end of proof. There are a number of ways in mathematics to write the end of a proof. You'll often see it written in QED. That's it's strange. English speakers the only people who end their proofs in another language, I think. QED stands for Quod erat demonstrandum, which means in Latin that which was to be demonstrated. That's like a little old-fashioned. The way you'll usually see textbooks ended is just with this black box. The black box has a couple of interesting names. It's most commonly called the Halmos after the mathematician Paul Halmos, but it also has the name the tombstone, and I think it's supposed to kind of call to mind the idea if I killed the argument. Sort of interesting. I remember a couple of years ago I had a student named Drew. I'll give him a little shout out here. When he heard that it was called the tombstone, he started writing it on his tests as a real tombstone, and I would see appear on his tests. He'd write a little like RIP, and sometimes he'd even decorate it with some flowers like that. So I often see when we're giving tests on paper and in person, I often see people end their proofs that way. No one in mathematics does that, but my students do sometimes. So you end your proof with a tombstone like that, and hopefully like just the square tombstone, you don't have to actually make the RIP mark. But anyway, this is a proof that we just did, showing that an improper integral converges. Note what this means. I was able to show this integral comes out to a finite number, even though I have no idea what that finite number is.